Okay, so the ICS 11. Yeah, I didn't really do anything particularly like this in the section. So the challenge is going to be to figure out what on earth does this thing look like, but more to the point, what qualitatively that I need to know can I conclude about this shape? Now, what it actually looks like, again, you don't necessarily need a really accurate picture. All you need is something that's good enough to answer questions about ranges of values. Right? So what's important to notice about this, look at our equation. So we have rho equals, rho less than or equal, pardon me. Then I have 2 minus sine phi cosine theta. Well, you could rewrite this in terms of x's and y's. It'd be rough. You'd have to take this, multiply both sides by rho squared. Then once you have a rho squared factor here, you could say, rho sine phi. Oh, wait a second. You could multiply both sides by rho. Let's just do this. Rho squared less than or equal to 2 rho minus rho sine phi cosine theta. Notice that that's x. This is x squared plus y squared plus z squared. And this, unfortunately, is a radical. But the point is you could convert everything into x's, y's, and z's at that point. And again, it'd be this nasty, nasty equation. Let me observe that there's a trickier way to do this. The trickier way is to say, I don't actually need to know exactly what this thing looks like. The point is, let me just kind of scratch all that off because I don't really need it. I claim that if you look at the equation, rho equals 2 minus sine phi cosine theta, notice that rho is always greater than 0. And it's always defined, and it's always a nice, perfectly decent positive number. So whatever direction you might be looking, be it in that direction or maybe straight up or down off at an angle that way, whatever direction you might be looking, you get a positive value of rho. So this thing, it might be lumpy, but in some way or another, it kind of envelops and goes all the way around the origin.
Remind me again, how do you get to that conclusion that rho is always positive?
Because 2 is bigger than this could ever be. Yeah, that's right. So that's right. So this is always less than 1. Yeah, exactly. So how do y'all feel about this observation? So I claim it has to go around the origin. Now, as opposed to what? Well, for example, as opposed to, like in polar coordinates, let's just look at a two-dimensional example. What if I had r equals 2 minus sine theta, for example? Well, it's going to be some sort of a lumpy. We could work it out and figure it out, but what exactly this looks like, I don't really care, because r is always positive, which means it kind of goes around the origin in some way. Maybe it's a little lumpy or egg-shaped or who knows what. Okay, but what it doesn't do is it does not do this. It doesn't do anything like that, because what's the value of r in that direction? Well, you'd have to have a negative r to sort of like this not sort of go around the origin. If r is always positive, then you're going to just, as r continues to be positive, as theta moves around, the path moves around the origin. And I claim the same thing's happening here. If rho is always positive, it's just going to, for different values of phi and theta, it's just going to envelop and wrap around the origin. So good news, because it wraps all the way around the origin, I claim that theta goes from 0 to 2 pi, and phi goes from 0 to pi. In other words, theta and phi take on all possible values. And so you get, let's see here, in your breakdown, rho squared sine phi d rho d phi d theta. Theta goes from 0 to 2 pi, because it goes all the way around, and phi goes from the top all the way around to the bottom, namely from 0 to pi. So we get 2/3 of our answer just from the observation that rho is always positive. That's a cool trick. It's a tricky observation, but it's cool. Let me pause, make sure everybody's on board. Is everybody good? Who asked me this question? I forgot. Yeah. Okay, right. Does that make sense?
Yeah, but I'm a little confused about why rho is larger than 0.
Why rho is greater than 0? So we have this formula for rho. Right? I just want to know what this surface looks like. Right? Now, what we're actually interested in, you're right, what we're interested in is where rho is less than that.
Yeah.
Right? So that means, in other words, what's inside of the surface that's defined by this. So I figure if I know what this surface is like, then I just want to know what rho is, what the points are that are inside of that surface. And on this surface where rho is equal to 2 minus sine phi, this is small. This is always less than 1 here. And so 2 minus something small is going to be positive. In fact, this will always be greater than 1, or greater than or equal to 1. Yeah. I mean, less than or equal to, this is always less than or equal to 1, so therefore rho is always greater than or equal to 1. Yeah. So this doesn't ever get anywhere near the origin. Okay. So the only thing that remains is to figure out the range of values here for rho. And, well, let's see here. Well, for any given value of phi and theta, I'm looking off in some direction. And rho is going to start at 0, and rho is going to end at a point like that, and that's a point that's on this surface. That surface has that equation, and so I need to solve for rho in this equation. Conveniently been done, right? Because we're clever enough to always use the rho on the inside, because rho is usually given as a function of phi and theta. And so this, we just get 0 to 2 minus sine phi cosine theta. And now we've got to put our integrand in here. And let's see, what was the we want to compute the volume, so the integrand's 1. Yeah. Does that make sense? Is that okay? All right? Okay.
Okay, so you're told that,
yeah.
Just that last statement you made, so if you're told it's a volume, you just can write the integrand as 1.
Yeah, that's right, because what we're computing, our original problem was this, right? And dV
Becomes
is all of that stuff there.
okay, cool.
Right. And so the only thing that we're multiplying by dV is 1. We're not, there's no extra factors. Yeah. Right. Everybody good?
So,
Yeah.
Area is 1 in xy. And then
Yeah, that's right. If you want to compute the area of something in the xy plane, then you're doing a double integral of 1 dx dy. That's right.
then the centroid is.
Centroid is different. Centroid is there's an integrand there. I mean, and there's a whole formula where you have to divide by the mass and stuff.
So you
So-
define the mass, do all
Yeah.
the calculation based on the picture you have.
Yeah, that's right. Yeah, but I mean, so for centroid, it's not really analogous. Computing centroid is not an integral of 1. It's just that you compute the area as part of computing the centroid. Does that make sense?
It's just like a rectangle in xy, the centroid for.
No, I mean centroid. Let me stop this recording, then I'll talk about that.